Now I may let me turn over the time to Professor David Wikowski to chair the rest 3 talks in the morning session. David, please.
So good morning, everybody. I'm David Wikowski, Associate Professor here at NTU. And I would like to introduce the next talk by Professor Ho. So Professor Ho is Emeritus Professor at National University of Singapore. He's also a fellow of the American Physical Society, and he received the National Science Award in 2006. So I know Professor Ho is some person that has devoted a lot of time for research, but also for education. And I think this is the topic of the talk today, because he will talk about Prof Yang and physics education in Malaysia and Singapore. May we now invite Professor Ho up on the stage, please?
Okay, thanks. Well, like many in the audience, I've been Professor Yang. I'm the great admirer. In fact, I'm a great fan of Professor Yang. He also helped me in my physics career, so it is my honor and then very happy to, in this occasion, to say a few words. Now, to begin with, I will just read out from the, I couldn't see, okay. So I just quote this Luis Alvarez Gomez, okay. Luis Alvarez Gomez is the, I think presently is the director of the center of the Simon Center for Geometry and Physics at the Stony Brook, USA. And then in 2007, Professor Yang was revisiting the sun, Geneva, and then he gave a public talk. And then at the beginning of the talk, then Alvarez Gomez have this say, okay? So let me repeat what he said, okay? Professor Yang is a living legend in physics. The depth and breadth of his contributions are simply staggering. He's the origin of the discovery of parity violation, Yang-Mills theory, with which we write the standard model, the Yang-Baxter equation in the theory of integral system, and the application of topology in physics, and along etc. and etc. And he's also an excellent speaker. You notice in this introduction, he highlights very 3 important contributions of Professor Yang, which I'm going to repeat. Okay. I would say this is, well, maybe the 3 miracle papers of Professor Yang. And then I think most of you, you're a physics student, you know that in 1905, Einstein wrote the 3 miracle papers, right? The first, the one on special relativity, one on the photoelectric effect, and one on this Brownian motion. So these are the 3 miracle papers. And the 3 papers just mentioned by this Professor Gomez, the first one is the Yang-Mills, which was published in 1954. And then the second one is the parity violation, which is 1957. And then the Yang-Baxter equation is 1967. Now, if you compare the impact of this Professor Yang 3 paper and then the Einstein 3 paper, I think they're comparable. And then, in particularly, you can almost match, okay, the Einstein special relativity and then Professor Yang-Mills equation. They all have long-term implication and usefulness in physics there. And then the Yang-Mills equation maybe more, okay, because it talks about the dynamics, rather than just symmetry alone in the special relativity. And then, of course, you have the photoelectric effects of Einstein. Then you can compare with the parity, okay, the violation of parity in 57. And the Brownian motion, you can compare with on statistical mechanics, you can compare with the Yang-Baxter equations. So they are comparable, okay? So let me revisit this 3 papers with you, okay? So first one is the 1954, which is Yang-Mills equations. Now, if you think about it, in the development of physics, I think nowadays we think development of physics start with Newton, right? Which is first published a Principia in 1687. That means 17th century. If you think about physics from there up to now, okay, and then you look at the deep fundamental level, then there are no more 5 fundamental equations. You can count, only 5. The first one, of course, is the Newton equation in 1687 for dynamics and also for gravitation. And then the second one is the Maxwell equation, which is published in something like 1865, which is unify electricity, magnetism, and light. And then the third one would be the Einstein gravitation, right, which is 1915. That geometry the whole physics there. Then the follow-up would be about 1926. You have the quantum equation, which is Schrödinger, Heisenberg, Dirac equation. There's the fourth one. And the fifth one would be the Yang-Mills equation, which is in 1954. These are if you think about it deeply, okay, these are the most lasting contribution in physics. Because even now, the way we do physics, fundamentally, okay, the equation of motion would be the most important. So in terms of this equation, and then you also think about the nature. And then as far as we're doing particle physics, the fundamental force only 4. And then the earlier ones you experience is when you come out from your mother womb, which is a gravitation. And then up to now, we don't still quite understand. But then gravitation, as I said, the equation is the 1915 in general relativity by Einstein, the gravity, okay? And then so that explains gravitation force. Now the electromagnetic force is accounted for by this Maxwell, which is about 1864 or 65, okay? And then now the other 2 forces, which is confined in a very short range, the weak force and then the strong force, which is Yang-Mills. So the Yang-Mills can account for the 2 forces, the weak force and then the strong force. So the impact, the tremendous contribution of the Yang-Mills fields in this, in our understanding of fundamental physics is enormous because it accounts for the weak force and strong force. And now there, of course, there's a unification. Then the electromagnetic force is, of course, is the simplest gauge field. And there are speculation that the gravitation also a gauge field. And okay, the next thing, or maybe I should say a few words about gauge field. Well, what is gauge field? I think probably I can quote Professor Yang again. I think he said the concept of gauge field in this slide in a very precise and easy to understand it there. Now, if you read this, then what he said, okay? Suppose you consider a sphere, a complete sphere, perfect symmetry, and you live on a sphere, then every point is equivalent. But then to do physics, you have to make your coordinate system. So you have to decide one point is north, one point is south. But then to choose which point is north or south is up to you. So that is a so-called, you say, a convention. So you have to make a convention to choose North Pole or South Pole. But then another person lives in the sphere. Also, he can also choose North Pole or South Pole. Right? So he has arbitrary choice. So that means there are tremendous number of the choice of North Pole and South Pole, depending on who is talking about. That means convention. So there are different, many conventions. Now, when you do physics, you have to communicate with each other. So you have your convention, and I have my convention. You have to communicate. And when you start to communicate, then that is gauge field. That's gauge field. So that is what Professor Yang said, that we are naturally led to the concept of gauge field. That is the, in a nutshell, the explanation of a gauge field. Sorry. Now I come to his second paper, 1956 with Li Zhendao. Now the parity violation actually means the mirror image, right? You look at a mirror every morning, then whatever you see in mirror is almost same as what you are in the actual world. Then so long time everybody said that the mirror world and then the actual world is the same. But then long time also people realized that in fact the phenomenon are different. I give an example, right? So if you are in the physical world, your heart is on the left-hand side in general. But then your image in the mirror is the right-hand side. So that means there is a difference between the actual world and the mirror world. That means the parity is broken. So that has been known. But you must realize that that breaking of parity is a phenomenology. It's not the fundamental law of physics. So what this 1956 paper contribute is that not just a phenomenon, it's the dynamics. And the dynamic is due to the weak force. It's the weak force dynamic that break the mirror symmetry or parity violation, which is much deeper than the phenomenon, right? So phenomenon is a superficial, and then the fundamental law is fundamental. And then let me mention the third one, which is so-called Yang-Baxter equation, which in fact is some sort of consistent equations there. And you look at the diagram, the left-hand side equal to the right-hand side. So it's something of shifting or braiding. And this equation was in 1967 paper when Professor Yang studied the one-dimension scattering problem in the presence of the so-called the delta function, the Dirac delta functions. So he come up with this consistency equation. And then after that, of course, Baxter, looking from another point of view, also arrived at the same equation. And that's why called Yang-Baxter equations. And then this one turned out to be very closely linked to mathematical structure, so-called Hopf algebra. It's not the Lie algebra, Hopf algebra. And then from there, now it's so-called the quantum group or quantum algebra. And there is, of course, some sort of solution called Yang-Gen, which is still mathematical at the moment, but then application for physics, many people are investigating and looking for it. So these are the so-called the three miracle paper. Now, with this achievement, then you can realize that Prof Yang achievement, of course, is transcend the Nobel Prize. In the year 2002, when the people celebrate his birthday, which is 80th birthday in Beijing, then you look at how many of Nobel Prize winner or Nobel Prize laureates attend this celebration, which is more than 10. So the figure speaks to how people respect, and then how Professor Yang and how important is his contribution to physics. Now, Professor Yang is not just confined to physics. Then when you talk to him, in fact, he almost knows everything. And then everything you mentioned, I think he will have some of his view. So I would say that he's a great thinker. And then that is not my view, okay? It's many other people's view. And then I will just quote one of his longtime classmates in Tsinghua when they were childhood, Xiong Bingming, about his other contribution. So let me read out. Xiong Bingming is an artist, I think, but by the way, he's gone. Okay? He said, Professor Yang's contribution have extended far beyond physics and mathematics to encompass the humanistic ideal of Chinese civilizations. So I will elaborate on this and give 3 illustrations. Now, this one is the sentence, just the one I just quote from Xiong Bingming, and then I think he used this Chinese poem. This Chinese poem is written by in the Song Dynasty by Lu Yu. I think you can read it. I don't want to translate it. I think the translation is there, and then the calligraphy is also there by Xiong Bingming. I like the last sentence. 诗记犹真造化功. Now, what are the 3 things that, apart from physics, Professor Yang interested and have important contribution there? There are many, of course. I just mentioned 3. First one is his opinion, his view on the I Ching, which is, I think it's a public lecture in Beijing in 2004. Now, I Ching have been with us, I mean, with China, in China, more than 2,000 years, and many versions, and thousands of people have tried to understand what it means. But people all agree that it is the core of Confucius thinking, Taoist thinking, and many branches of thinking. So that's why I say Prof Yang is a great thinker. Now, his view of the I Ching is not just to interpret the I Ching. He talked about the impact of I Ching on the Chinese culture. I think that he talked about 3 things. Okay? First is because of I Ching development, that the Chinese syllabus is a monosyllabus. So Chinese like table is zuo, is single, so it's a monosyllabus. And then he traces because of the early days of the I Ching. So that is on Chinese language, character, and so on. The next thing is that the conceptual development of Chinese thinking about the nature, the beauty of the nature, he thinks also that is motivated by I Ching. And lastly, he touched on the important question that people ask, okay, why the technological aspect of China, in fact, is long developed and far exceeding the Western world. But then the pure scientific reasoning, the sophisticated science, is not studied in China, okay? And so he said, you look about the I Ching, the whole thinking mode is more inductive thinking and inductive reasoning. The lacking is the deduction. By deduction, he means the mathematical, logical deduction. It's not just the simple deductions. And he said, because of this, the lacking of the deduction, then that somehow delayed the sophisticated science development in China. Because in science, then you need induction, you also need the deductions. So this is his view, and then I think it's fundamental and then important. It's different from what the usual people study from I Ching. As I said, there are 1,000 people of scholars working on I Ching, but this view is very original. The other thing is that I think he's a poet also, and then he gave a public discussion with Fan Zhen. Fan Zhen, of course, many of you know, he's a famous artist in Tianjin Nankai. And then they have a dialogue in the 2008. And then I think it published in a small book. I think if you have time, I would recommend you to look at it there. In this discussion, he discussed the concept of beauty in different contexts, starting from the poem, and then the painting, sculpture, and so on, until the physics. And then in particular, he used the rainbow, the inclination angle, so on. You can calculate from the Maxwell equations. So that is, in other words, the beauty is tie up the humanities and then the physical science. Now the third one is quite recent, which is in 2020. He talked about Weiqi. Now Weiqi, what is this problem? This problem say you have n black one, the cheese, okay, the black pieces on the left hand side. You have n white on the right hand side. And then you come together, okay? And then you district the movement. You interchange only in the nearest neighborhood, right? And so that after all this interchange, you got the black, white, black, white, black, white next to each other. And then you have to do it with the minimum number of moves. Right? So this is a problem. Now, Weiqi is a long time in Chinese culture and so on. And then, but this problem was, how do you do rest it? I think it was rested, I think probably in Kangxi. That means, or Yongzheng, that means it's about the end of 17th century. But people doesn't know how to do it. But then nearly about 80 years ago, there's a very famous mathematical statistician, okay, and a very famous Chinese scholar, Yi Pingpe, and so on. They know how to solve it. They discovered how to solve it. But then the solution was not written down. And Professor Yang mentioned that when he was a student in Sinanenta, he thought about this. I think he also spent some time with it. I don't know whether he got a solution. But when he go to US, he also got a solution, but he forgot to written down. So in the 200, sorry.
Overhand for 2 minutes.
Okay, sorry, thank you. Yeah. 2020, he sort of got this solution. So my time coming up, let me, how many minutes more I have?
-2.
Huh?
-2.
5 minutes?
No, you already overwhelmed your time, but 1 or 2 minutes if you can.
Okay, 1 or 2 minutes, okay. Okay, I think the rest I want to speak about Professor Yang is let me quote this one. This is important about the Yang. And this, I quote this from this Lin Yitang. Lin Yitang is the first president of the Nanyang University. He said about the great souls, okay? Great souls react in a particular way to their social and scientific environment and make it of important to us. They have the quality of genius which affects and is affected by the things they touch. In them is lived to its full life of their age or generation. They absorb all there is to absorb and respond with finest and most powerful sensitivities. Right, and then I'll try to finish. In fact, the rest, what I'm going to say is already said by Professor Ling San and also Professor Po in this morning talk. So I think I will just skip through and then to come to somewhere I think Professor Yang's contribution in the research education in Singapore, he led a very good, strong research group in so-called the Choo model, which is led by Professor Yang. And then he also started with the so-called AAPPS society and so on, try to unify, try to put all the physics society in Asia. And then this one also, the Tangkaki, and then he also visited the Penang, and then they become external examiner and so on. And then there's a strong group of the gauge field theory in the USM at that time, and then it still continue. So I think I'll probably around the time. I think I will just cut it short. Okay. Okay. Thank you very much.
Good. Thank you, Professor Ho, for this very inspiring talks about the work of CU Nanyang and also all these cultural aspects that I was not aware of personally. So maybe we can, if there's any question, we are a bit late, but we can still take one or two questions. So if not, there is some question online, so let me read it for you. In today's context, most physics students share a common sentiment that what they are taught is valid permanently. But new development in physics could lead to the discovery of flakes of our current physics knowledge. Any thought on this, and how will it change the way physics is taught?
I'm sorry, I can't catch you. My ear is not so good. Can I read the question?
Yeah, sure.
Yeah, can make it bigger. My ear is okay. Most physics students share a common standing.
It's about evolution.
New physics and discover flow occurrences and thought, how will it change the way physics taught? Well, this is I think he's asking the question how the physics taught, because there are many changes in physics there. I would know nowadays, suppose I take say, for example, a particle physics and so on, we still follow teaching the concept, equation, and motion, and so on. So but then there's many changes in physics there. So you have the algorithmic physics using computer and so on, and then you may be able to do our differential equation and physics and so on. So how will be physics taught in the future? That, of course, depends on how we understand physics there. Fundamentally, from the Newton up to time is almost the same. But then now, of course, there's the dark matter, dark energy, and so on. So how physics taught is just, I think, would be just speculation. Okay.
Okay, I think thank you very much, Prof. Ho. I think we should close the Q&A session and move to the next talk. So let's thank again Prof. Ho